Hi, you're ready to do the power drag. On your table, you should have some tools. You will have an 18th scale vehicle. We're not quite ready to use the 10th scale ones yet. You will have a digital scale, some masking tape, and weights. Yours are probably washers. I just happen to have these lying around. Now, your job today is to figure out how much weight you can carry from one point to another point, but still go fast. And the place you might see this is the mail carrier. He's got to carry mail from Boston to California and Pomona, and he needs to know how much mail can go in that truck, but he's still got to get it there pretty quickly, or the recipients are going to be angry that they're not getting their mail. This happens with anybody who carries cargo in any Mack truck across America. So, how are we going to do this? We are going to start by getting a baseline and knowing how our cars drive with no additional weight on them. That's important. We need that so that we can start our coordinate plane data graph at the end of this. All right, so let's take a look. First thing you're going to do, turn on your scale. I'm letting it go to 0 so that it will calibrate and get a good weight. We also want to know that it says ounces. Yep, this one already does. If it doesn't, you'll push the units button until you see OZ for ounces. Then you can put a car on. This car weighs 15 ounces and 15 hundredths of another ounce. So 15 ounces, 15 parts of another ounce. The 15 parts of the other ounce are very important because as we start adding weight, you might be adding something that's just 2 or 3 ounces. Okay, now you have the weight. Be sure to write that weight down on your data sheet. Yours might not be green, but it will look something like a chart like this. So weight is going to be in the second column here. Put OZ for ounces just so next week when we go back we won't think it was kilograms or something. All right, I have my weight for my car. Now, you're going to need to take your team up to the start line, and you're going to time the car. Having 4 or 5 timers is better, but 3 is okay, at least 3. If there are not enough people on your team, then recruit some other people to come time for you. All right, most of the timers have a blue button for start and stop. Start, stop. And the one under your index finger resets everything to 0. So start, stop. Now let's read this one. It says 1 and 63 hundredths. So that's 1 second and 63 hundredths of another second. Got to write down the 63 hundredths. So you would write 1.63 on your data sheet where it says time 1. Write down all the times that were taken on the stopwatches. Now head back to your desk and you're going to calculate the average time. That's just in case somebody has a really slow trigger finger. Or you're going to possibly work on finding the speed and the work of the car. That's up to your teacher. She'll tell you whether she wants to go ahead and do that or wait a little while. And after everyone in the group has taken their turn and gotten their data, we'll get back together and I'll show you what to do for the actual power drag. Okay, teachers, press pause. All right, we're back. You have now driven the car and you see that it does not drive very well. What happens is these are pretty slick tires and your floor is also pretty dusty probably. Every school is. So you're not getting any traction. There's no friction here. That's why we love using these cars. They actually need some weight in order to drive well. This first time around, we're going to assign the weights. That way we can get a good range of numbers, because without a good range, we don't have any idea how to set up our graph at all. We don't know what intervals to use along the x-axis or along the y-axis. So, first thing you're going to do is add weight to the car. This time we're going to assign the weights. In a few minutes, you'll get to do your own weights. All right, first group, you're going to add enough weight to equal 30 ounces. That means the car and the weight taped on the cars add up to 30 ounces. And that's how you're going to do it. It's very low-key and simple. Make sure you use a lot of tape if you need it, because once the car starts driving, things sling around and it will affect your driving and your times. You are going to put the car down at start, time it from start to finish. Make sure you grab your car and turn it off, because once you cross that finish line, you're just wasting batteries if somebody has to go chasing the car. All right, 30 ounces for the first group, then 60, another group 90, 120, 270. By the time you hit the 270 range, you're going to need to add some textbooks to the car. They just don't get heavy enough. If you have 6 groups, you might want to add 180 ounces in there also. So 30, 60, 120, 180, 270. After you have done that and calculated, again, the average time and the speed of the car, you might want to go ahead and do the calculations for work. And those can be found on this sheet that says calculate. If you need a little reminder about averaging, that's also on here. Make sure you get all that stuff on your data sheet, and then you get to come back and do your own weight. So go ahead, let all the teams do their assigned weights at 30, 60, 120, 180, 270. And then once you're done and you've gone back to your seat, your pit area, you can choose a weight. We're not telling you how much at this point to do. You'll have a chart up on the board that shows what the speeds are and the weights are, because people are going up to fill them in as they go. But this one's up to you. We're also not telling you where to put it, although you should have taken note of how the car was driving. And hint, hint, this is where the power is coming from in the car. Your engine, your motor is back here. Weight up here? No, it's not right here. So go ahead, get your baseline weights at 30, 60, 120, 180, 270, and then you get to choose your own weight. And when you come back, we'll talk about how it all looks on a graph. Press pause. All right, now we know how fast the car can go with no weight. We've got a pretty good idea of how fast the car will go with a bunch of weights, and how much weight is too much weight. So, depending on the surface you're using, it may have been a lot less than 270 ounces, or maybe more, but you have the range of weights sitting on your charts. Now, teachers, here's where we need to go ahead and set up our coordinate plane, our XY graph. Simple way to set up a graph. You can laugh at me if you want to, everybody does. But trust me, you'll remember this. All right, make an X, squash it. The X is the horizontal axis. That is your independent variable, is the thing you change. You can remember that by, make this a capital I. There's the top of the I, here's the bottom of the I. Squash it. This is your independent variable. That's what you changed. In our case, we changed the weight of the car. Now the other axis is the y-axis. Here's your y. It goes vertical, up and down. The y-axis is the dependent variable. Once you've done something like change the weight, there's an outcome. The outcome is what we put on the y. In our case, it's our power factor. You might also want to set up graphs to do speed, to do distance, to do work. There are a lot of different things you can work on. Right now we're going to concentrate on just setting the one up for the power score. All right. Now, you have a range of values. The easiest thing to do is to take a look. I just have an X and a Y. I know they start at 0. Now, if you're talking about slope, that's a whole different issue. And we'll talk about that a little bit later, but right now just start at 0. I know my weights went all the way up to maybe 270 or 300 ounces, so I can end there. And I know the scores are going to top out somewhere in the 3,000 range. Yours probably did too. So now you just need to choose some intervals. What are the easiest intervals? How are you going to count? By 2s, by 10s, by 20s? What are you going to do in order to get from here to there and show the data? There's no magic formula. I know when I was in school, I would get nervous thinking, how do I know whether I use 20s or 40s or 50s or 100s? Well, you don't until you have some data. and you know what you need to show on the graph. In our case, easiest thing to do is probably go by 20s on the weight, so 20 ounces, 40 ounces, 60 ounces, and by 500s on the y-axis. That's how I've done it. You can set it up any way you want, as long as X and Y are in the correct spots. So, teachers, go ahead and on the board right now, go ahead and set up your XY coordinate plane, or in our case, the scoreboard, and have everyone start telling you what their weight of their car on your x-axis. Now move up the line until you get to the power score. And then you'll take a look at what shape all of that is coming out on this graph. We call this a Goldilocks problem. Some weight is too little. Some weight is way too much. What you want to know is what's just right. And the only way to tell that is by looking at a graph and analyzing the data. So go ahead and set up your graph, and when you're done, you can press play again, and Professor Pi will help you take a look at all those numbers and figure out what they mean. All right, thank you, and press pause.
You've run your RC car in an effort to win the Delivery Company Challenge. That is the greatest weight carried the longest distance in the least amount of time. But how do you know you're winning? Well, that's simple. Your team has a better score than any other team in units of ounces, inches, and seconds. Also, it's easy to see if your team is the highest score in your class, because then everyone on the team will have earned a scientific light and illustration drawing pencil. You get the pencil, not the car. The language of science is mathematics, and we'd like to describe the run of our RC car, which is a scale model for a delivery vehicle, in that language, namely mathematics. Graphs are the easiest way to communicate large amounts of information most clearly with the least effort. The RC car we're using in testing was approximately a 1 to 20 scale, as a real full-scale car like this one has a wheelbase of 102 inches. Look it up on the internet. That's the distance from the center of the front wheels to the center of the back wheels. Now the RC car measures 4 7/8 or 4.875 inches. That calculates to 102 divided by 4.875, or about 21. We're going to approximate that as a 1 to 20 car just to make the arithmetic easier. Now you'll have to make your own measurements and calculation for the car you're using, because they're all different. First, we'd like to plot speed as a function of added weight, as cargo weight. A general observation is that as more weight is added to the car, it will slow down, but we need numbers to turn that into a graph. To set the range for the graph, a couple of tests will be sufficient. Time the RC car making a run of the planned distance with little or no added weight, and then make another run with a significant amount of weight. Now, while software such as Excel will allow you to easily change the scale on a graph, drawing it by hand requires that you set the scale range before you start adding data points. No magic to this in finding a scale. When we had done our data, we had about 55 inches per second was the average speed of the car. And so here, 2, 4, 6, 8, 10. If we make that 50, then each one of these marks I've just marked off is 10. So 10, 20, 30, 40, 50. That'll be 60, the top speed of the car. It's around 65, and by the time we got out here to 40 or 50 ounces, it was going pretty slow. So if we go 10, 20, 30, 40, 50 for ounces, that'll get us down here, and it looks something like that. Now when we use that same information, when we're going, just pick some numbers here, remember we multiply the speed times the weight, so the weight's going up like so, which means that somewhere in the middle here is going to be the optimum. So if we take 40 inches a second and something like 30 ounces, 40 times 30 gives us 1200, is going to be the top speed. So when we go now to make a score chart, we want the vertical scale to go to at least 1,000, more, if not more. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would be 1200. And that's ounces per second. And the weight out here was 50 or so. So 10, 20, 30, 40, 50 ounces. This is my car. This is our little 20th scale car. The 10th scale, 16th scale cars that you're running are going to be much larger. The scale will be bigger. Zero weight, 10. This is in ounces. This is in the score, inch ounces per second. And you just have to take the data. Mine looked something on the order of, so that was 1200, 1, 2, 3, 4, 500, 6, 7, 8, 9, 10, 1,000. We had scores that looked something like that. And this is cargo weight added. As I say, yours will look different because the scale of your car is different. So that's how it's done. The 1/20th scale car, with no cargo weight added, had an average speed of 54.5 inches per second over a 120-inch run from a standing start, and had a top speed of about 65.65 inches per second. To scale, a 1/20th RC car going 65 inches per second is equivalent to 74.6 miles per hour for a full-scale car, and that's obtained in just over 1 second. That's an acceleration rate only seen in funny cars, top fuel dragsters, and F1 race cars. Now, if we're working for a real trucking company, they'll calculate the same challenge, but they will use units of tons, miles, and hours. We've used a 1/20th scale car for our testing, and the RC cars at West Mecklenburg are about 1 to 16. So how fast did your RC car travel, both on the floor in true length and to scale? If you were sized to the scale of your RC car, that is 1/16 the size you are now, how fast would it appear your car is going? Now in our little model, our cars were parked 20 feet apart in scale. If you're standing on top of a 10-story building, it looks like this. But if you're down at the level of the cars, then it looks more like this. What did we see? It looks as if the car is going incredibly fast. And to scale it is. A scale speed of 70 miles per hour after 1 second acceleration, that's accelerating as fast as funny car dragsters, top fuelers, and F1 cars. But when we watch from our full-scale perspective, it doesn't look so fast. So let's use the language of science to describe what we see taking place. Now we want to draw a science math picture of what you have seen, and that means make a graph. The RC car starts out, we can see from the video of the time code that the car crosses the 1 foot line at 0.47 seconds. At the 2 foot mark, the elapsed time is 0.74 seconds. And at the 3 foot mark, the elapsed time is 0.91 seconds. And finally, at 1.1 seconds, we're out to the 4 foot mark. Now, we've been using a digital camera as a stopwatch because we get both an image of where we are as well as the time code when we play the video back in Windows Live Movie Maker. It's a free add-on in the Windows XP or Windows 7. But now we want to make an XY plot of the data points we've collected. Namely, the points are 0, 0, 0.47, 1. Third one is 0.74, 2, 0.91, 3, and 1.1 comma 4. And here's what it looks like when we make a plot. After a time of 0.91 seconds, or about 1 second, and a distance of 2 feet, it would appear that the distance increases linearly as a function of time. And the slope of the line, that is the distance on the y-axis, as a function of time on x-axis, is 5.55 feet per second. That's the speed of the RC car after it has accelerated up to full speed. You'll notice the data is not linear from the start at time 0 up to a time of 0.9 seconds and a distance of 2 feet. One of the very next algebra objectives that you'll cover is to compare linear and nonlinear equations. And this is an example of why you'll need to understand that sort of function. Now in this event, we're starting the RC car from a standing start. They accelerate for a period of time and then reach their maximum speed. When we divide the total drive distance by the total measured time, that gives you an average speed for the trip. It's not a constant speed, but it's an average for the whole trip. Now you're making a road trip and you stop for McDonald's and you stop here and there, slow down, speed up. And at the end of the day, you look at see how many miles you've traveled in 8 hours. 8 hours. So you've traveled 480 miles in 8 hours. Your average speed is 60 miles per hour. It means at times you're traveling 70 on the interstate where it's allowed. Other times you're sitting still having lunch. The point is, a graph will allow you to handle all of these situations, and it compresses in a huge amount of information in a very small and efficient package. It is an essential skill you must learn. So now let's see you win the delivery driving challenge, and we'll award my scientific light and illustration pencils to the teams that do.